Stand a small glass beaker upright in a bath of liquid helium below about 2 Kelvin, with the beaker's rim well clear of the surface. Come back in a few minutes and the level inside the beaker has dropped. Come back again and there is a drop hanging from the outside of its base. It falls. Another forms. The beaker is emptying itself over its own rim, uphill, through a film about 30 nanometres thick, 100 atoms deep, invisible, coating every surface in the cryostat. Nothing is pumping and nothing is pushing. It does not stop until the beaker is dry.
And at the end of last time, you said the reason without knowing what you were promising. The order parameter of that liquid is a complex number, a magnitude and a phase, and a flow is that phase winding as you walk along the pipe. Everything today follows from one sentence. There is a single angle defined everywhere in that beaker, and it must come back to itself when you go round a loop. Last time that was a picture. Today it makes numbers.
Before it does, be honest about the film. Is the climbing the deep part or the showy part?
The showy part, and better to concede that in the first minute. Helium wets glass, so a thin layer sits on every surface standing above the liquid. And it does that above the transition too, where nothing happens. What changes below the transition is that the layer has no viscosity, so nothing pins it to the wall. A film that can flow freely is a siphon. Bernard Rollin argued for it at the Clarendon in Oxford in 1936.
So the film is a delivery mechanism, and the thing delivered is the absence of drag. Where did the absence of drag get established? A beaker draining itself is a demonstration, not a measurement.
On the 8th of January, 1938, on two facing pages of Nature. Page 74, Piotr Kapitsa in Moscow. Page 75, Jack Allen and Don Meisner in Cambridge. Kapitsa's apparatus is worth holding because it is so plain. Two polished glass discs clamped with a gap of half a micron and helium made to flow out through it. Above the transition, almost nothing gets through. Below it, the liquid pours, and he bounded the viscosity at least 1,500 times lower.
And Allen and Meissner were doing the same experiment in a different geometry. So what did the capillaries add?
Something stranger. They found the flow rate barely depended on the pressure driving it, or on the width of the tube, and that is not a small viscosity, because a small viscosity still gives a rate proportional to the push. Their liquid speed through a channel was set by something else entirely, and that something else is the second half of this hour. Kapitsa coined the word in the last sentence of his paper. By analogy with superconductors, the helium below the lambda point enters a special state which might be called superfluid. He had half the Nobel Prize in 1978. Allen and Meisner did not.
What did people already know before those two letters? The temperature seems to have had a name before anybody knew what happened at it.
It did, and the name came off a graph. Willem Keesum and Klaus Clusius measured the heat capacity of liquid helium in 1932 and found it doing something violent at about 2.17 Kelvin, rising steeply, peaking sharply, dropping on the far side. Ehrenfest said the shape resembles a lambda, and the temperature has been the lambda point ever since. Now read the graph as a physicist. A sharp peak and no latent heat. By the classification you gave me, what is that?
Continuous, not first order, no heat absorbed at fixed temperature, no coexistence, no supercooling, nothing to nucleate. The order parameter grows out of zero instead of jumping, so there is a broken symmetry down there, and something is making a choice, and I want to know what, because I cannot see what a liquid has left to choose about.
You will have it in 10 minutes, and it is nothing you can point at. First, the peculiarity that gives helium the chance at all. It is the only element that does not freeze. At ordinary pressure, it stays liquid all the way to absolute zero. You need about 25 atmospheres to make it solid. The atoms are light and the attraction between them feeble, so their quantum jiggling is comparable to the depth of the well holding them, and they never settle into a lattice. Which leaves the one thing you need: a liquid, still liquid, where quantum statistics have taken over.
And somebody made the connection to Bose and Einstein straight away, I take it. A fraction of the particles agreeing to occupy one state is exactly the sort of thing a broken symmetry would need.
Within months. Fritz London, in Nature, 1938. Bose and Einstein had shown in the mid-20s that a cold gas of non-interacting bosons does something odd. Below a critical temperature, a finite fraction of the particles pile into the single lowest state, and the fraction grows as you cool. London took the formula for that critical temperature, which contains nothing but the particle's mass and the number per unit volume, put in the helium atom and the measured density of the liquid, and got 3.1 Kelvin, against a lambda point of 2.17.
Close enough to be a real argument and far enough off to be attacked. What is the defense?
That the formula describes particles which ignore one another, and helium is a dense liquid whose atoms are very much in each other's way. Half again too big, with the wrong model, is the correct outcome and not an embarrassment. And it is the right instinct for one reason. Helium-4 is a boson. 2 protons, 2 neutrons, 2 electrons, everything paired, integer total spin. Which sends us back to the one line from our second conversation that this whole hour stands on.
The amplitude to add a boson to a state grows with the number already in it. So they prefer to be where they already are, and a cold gas of them piles into one state rather than spreading out. It was flagged at the time as something we would come back for.
And here we are. So the proposal on the table in 1938 is a macroscopic number of helium atoms occupying one and the same single particle state. Be careful what that buys. The natural next sentence is wrong, and we spend 20 minutes finding out how wrong.
Say what the object is first. If a huge number of atoms are in one state, what am I actually allowed to write down?
One function of one position. A general state of 100 million atoms is a function of 100 million positions. The wall from our first hour. If they are all in the same single particle state, the entire many-body state is specified by that one mode plus a count. Multiply its squared magnitude by the number of atoms, and you have the density of the liquid at each point, which is something you can measure with a ruler.
So it is a wave function carrying the dimensions of an ordinary fluid density. And I take it the phase is the interesting half, since you have mentioned it twice and delivered it never.
The phase is the entire subject, and here is what separates it from every wave function you have met. An ordinary wave function's overall phase is unmeasurable, but this is not a probability amplitude for one particle. It is an order parameter for a chunk of matter, and its phase is the choice the system made, exactly as a magnetization direction was last time. The wine bottle still applies. The trough is a circle of equal energy states, and the angle round it is the phase.
What symmetry got broken then? For iron, it was rotation in space, and I could point at it with my hand.
You cannot point at this one, which is why superfluids are harder to teach than magnets. The symmetry is the freedom to multiply the whole wave function by a phase factor, to advance every atom's internal clock by the same angle. The laws do not care, nothing measurable depends on it. In the ordered state, the system fixes that angle at a value it had no reason to prefer and holds it across the beaker.
I need an avatar, because advance every atom's internal clock is a phrase and not a picture. What is physically different about a beaker in which that angle is fixed?
This is the hardest idea in the hour, so we go slowly. Every atom carries a clock. Above the transition, the clocks run independently, and the time at this end of the beaker tells you nothing about the far end. Below it, they are locked. Nobody outside can read the time, That is, the unmeasurable overall angle, but everything inside agrees on it, across centimetres. And there is a price, which is the strangest fact in this hour. The phase and the number of atoms are conjugate, the way a position and a momentum are. A region with a sharp phase does not have a sharp number of atoms in it, which is why this broken symmetry is tied by a theorem to conservation of particle number.
That cannot survive a sealed flask. I can count what I put in.
You can count what is in the flask, and the flask is not where the phase lives. The phase belongs to a region, and a region trades atoms with the rest of the liquid freely, so its number is uncertain and its angle correspondingly sharp.
How can an angle nobody can measure be the thing that matters?
Because nobody can measure it, and everybody can measure its differences. Hold that shape. It recurs in every remaining conversation in this series. The way it changes from here to there is a velocity. The way it changes as you walk once round a ring is an integer you can count. Absolute phase, nothing. Phase differences, everything.
That is the claim I want you to earn, and I do not yet see what would let you write an equation for such a thing.
Then let us write one, the way you would if nobody had done it before. We want an equation of motion for a complex function of position and time. Guess the shape first. What single equation in physics governs a complex function of position and time?
The Schrödinger equation, which is a strange thing to reach for because Schrödinger's equation is about one particle, and this is a beaker of liquid helium.
It is strange, and the strangeness is the physics. Hold the objection, we build first. First term. In an ordinary Schrödinger equation, what is the kinetic term actually doing?
Charging for curvature. A function that bends sharply in space costs energy, and the sharper the bend, the more it costs. With the mass in the denominator, so heavy things are stiffer. That is the term that makes a particle in a small box expensive.
Take it over unchanged, with one substitution. The mass in it is the mass of a single helium atom, not the mass of the fluid. That will matter enormously in 20 minutes. Second term. The liquid is in a container, or, for the cold gases at the end, in a bowl made of laser light. What does the equation need to know about that?
Only the energy of sitting at each point. Wherever the walls or the trap push, add the potential energy of being there. Standard, and I would not expect it to do any work.
It does none until you reach a trapped gas, where it sets the shape of the entire cloud. Now the term that is not in Schrödinger's equation, and I want you to build it rather than receive it. The atoms repel. Two helium atoms at close range have a hard core and cannot overlap, so crowding costs energy. Ask what one atom feels.
The repulsion from every other atom, which sounds like the disaster from our second conversation. Every pair at every separation, a number of terms going as the square of the number of atoms, and none obviously negligible.
Except for one fact about this particular force. It is short-ranged, not screened the way the Coulomb interaction was in a metal, but short-ranged from the start because it is the overlap of two closed electron shells, and that dies within an ångstrom. So ask again, and let the shortness do the work. If the force reaches only as far as the nearest atom, what does one atom feel?
Only what is at its own location, not the distribution of the whole liquid, just how many other atoms are right there. So the energy cost of being at a point is proportional to the density at that point. More atoms here, higher energy here.
That is the term, and you have written it. In the equation, the density at a point is the squared magnitude of the very function we are solving for. So the potential energy contains the wave function's own squared magnitude multiplied by one number saying how hard the atoms push.
Which makes the equation non-linear. The wave is moving in a potential made out of itself.
The wave is moving in a potential it is making. Say back what we assembled. in a sentence before I name it.
A Schrödinger equation for one complex function standing in for the whole liquid. The ordinary term charging for curvature, the ordinary term for the container, and one extra term in which the condensate pushes on itself, proportional to its own density, with a single coefficient measuring how strongly the atoms repel.
That is the Gross-Pitaevsky equation. Eugene Gross and Lev Pitaevsky, both 1961, independently, on opposite sides of the Iron Curtain, and both wrote it down to answer the same question. Gross's title is Structure of a Quantized Vortex in Boson Systems. Pitaevsky's is Vortex Lines in an Imperfect Bose Gas. Neither was after a general equation for condensates. Both wanted to know what a vortex looks like.
Interrogate the nonlinearity for me, because it is the one genuinely new thing in there. What breaks?
Superposition breaks, and that is not a technicality. In ordinary quantum mechanics, given two solutions, you have their sum. Not here. Add two solutions, and the self-interaction produces cross terms that were in neither. So this is not a quantum amplitude in the usual sense. It is a classical field equation for a macroscopic object, closer to the equation for a sound wave than to the equation for an electron.
Then where does its authority come from? You called it a Schrödinger equation, and now you tell me it is a classical field.
From a mean field approximation, and the label matters. Each atom is made to feel the average field of all the others, Weiss and Landau from last time, in a new setting, with the same weaknesses. It is exact in one limit, a dilute gas, where the spacing between atoms is far larger than the range of the force, so an atom really does see only an average. That limit is not liquid helium. Helium is dense and strongly correlated, and the equation is a caricature of it. Good for pictures, poor for numbers. The limit is met almost perfectly in the cold atomic gases, where it is quantitative to a few %. So I am building on helium and caching on rubidium, and you should know that is what I am doing.
Then get one number out of it. So this is not only an assembly job.
One number, and the rest of the hour uses it. Two of the terms are in competition. Suppose something forces the wave function to 0 at a point, a wall or a defect. The curvature term hates it. Making the function change over a short distance is expensive. The interaction term is relieved by it. Fewer atoms there, less repulsion. So there is a distance over which the fluid recovers from being pushed to 0, set by those two costs balancing.
Which is a length built from the mass, Planck's constant, the density and the strength of the push. And since it is the only length the equation contains, anything in this problem that has a size has that size.
Anything at all. It is called the healing length. In liquid helium, it is about an ångström, the size of an atom, which is itself a hint that helium is not really in the regime where this equation applies. In a cold gas, it is a fraction of a micron, which you can photograph. And one more thing falls out that closes a loop from our first hour. Ask the equation for the speed of a long wavelength ripple in the density.
A sound speed. And the recipe from that first conversation was the square root of a stiffness over a density.
Which is exactly what comes out, with the interaction term playing the stiffness. The sound speed goes as the square root of the interaction strength times the density over the mass. Nikolai Bogolyubov got that spectrum from the dilute gas in 1947. Remember that the interaction is what put the sound there. It is about to become the difference between a curiosity and a superfluid.
You have promised the phase 3 times and delivered density every time. Where does it finally enter?
In the current, and this step pays for everything. Write the function as a magnitude times a phase factor, an amplitude and an angle at every point, and ask how much fluid flows past a given point. In ordinary quantum mechanics, that is the probability current. I am not going to do the algebra. What it would show you is that the magnitude cancels out, and only the phase's rate of change survives. And what survives has a completely different status from a probability. It is the velocity of the actual liquid, in meters per second, equal to the rate at which the phase winds as you walk in that direction, turns per meter, times Planck's constant over the mass of one helium atom.
The velocity is a gradient. Then the first consequence is mine, I think. A field that is the gradient of something has no curl. It cannot circulate locally. So a superfluid cannot rotate.
It cannot rotate the way water rotates. Put water in a bucket on a turntable, and after a minute, the whole thing turns as a solid body, every element spinning about its own axis as well as going round. A superfluid is forbidden that. Spin the bucket slowly, and the liquid sits there, flat, while the walls turn around it.
Is that a real experiment or a thought experiment? A liquid sitting still while its container turns is the sort of thing people describe, and nobody has done.
Real and done. And above a threshold rotation rate, something else happens, which is a section from now. Now the second consequence, which you should derive rather than receive. Take a closed loop inside the fluid, a ring-shaped channel with helium going round it. Walk once round, back to where you started. What is the phase obliged to do?
The wave function is a single function of position, so on returning to my starting point, it must have the value it had, which means the phase must have come back to itself, not to any old value, to the same angle. And an angle comes back to itself if it has changed by a whole number of turns. So, going once round the loop, the phase can only have wound by a whole number of complete revolutions.
Keep going. You have the winding. Turn it into something with units.
The velocity is the rate of change of the phase times Planck's constant over the atomic mass. So, adding the velocity up all the way round the loop is adding up the total change of phase times that same constant, and the total change of phase is a whole number of turns. So, the velocity integrated round any closed loop, the circulation, is a whole number times Planck's constant divided by the mass of one helium atom.
A whole number times a fixed quantity built from Planck's constant and one atomic mass. Put the numbers in. About 10 to the minus 7th of a square meter per second. Not an effect hiding under an experiment, a quantity a laboratory can measure, and a prediction that flow round a ring comes in units.
The mass of one atom. Not the mass of the liquid, not some effective mass. Why should a property of a whole deal beaker be scaled by the mass of a single helium atom?
Because the object carrying the phase is the single particle state they all occupy, and that state belongs to one atom, which makes the quantum of circulation a measurement of what is condensing. The same argument gets a factor of 2 in a superconductor and proves the electrons are paired. One number, decisive, next time. Here it says helium-4 condenses one atom at a time.
Who saw it first and who measured it? A prediction in whole units is only worth something if somebody went and counted the units.
Lars Onsager said it aloud in 1949 as a discussion remark at a conference in Florence, printed in the proceedings and nowhere else. Circulation is quantized, in units of Planck's constant over the mass of one molecule. He never wrote the paper. Feynman rediscovered it independently, published it in 1955, and built the picture of a vortex tangle on it. Joe Vinan measured it in 1961, a fine wire down the axis of a rotating helium container, plucked so it vibrates. Circulation around the wire makes the two circular polarizations travel at different speeds, so the plane of vibration precesses at a rate that gives you the circulation, in units at the predicted size.
There is a hole in my own argument, and I would rather plug it than have you find it. I said the phase must come back to itself. That is only true where the phase is defined. Where is it not?
Precisely where the magnitude is 0. Where the wave function vanishes, its phase is meaningless. There is no angle. So a loop with non-zero winding must enclose somewhere the density goes to zero, and by continuity, that somewhere is a line running through the fluid. That is a vortex, an empty core, the phase winding once around it, the fluid circulating faster the closer you get. And its thickness is the only length in the problem.
The healing length. So the core of a vortex in liquid helium is 1 atom across, and Gross and Pitaevsky both went to the equation for exactly that reason.
For exactly that reason. A vortex is the one object whose structure the equation genuinely has to compute, because the linear terms alone cannot decide how fast the density recovers.
Now the question the whole hour is aimed at: why does the flow not stop? Every other fluid I have ever met eventually stops.
And I want Landau's argument rather than a picture, because it is the most economical thing in the subject. No model of the liquid, no equation of motion, only bookkeeping. A superfluid at absolute zero flowing down a tube. Equivalently, an object dragged through it. For the flow to slow, energy must leave it. Where can it go?
Into the liquid. And at absolute zero, the liquid is in its ground state, so the only thing energy can do is make an excitation. There is nothing else on offer.
So whether a superfluid can decelerate is whether it can make one excitation. Arithmetic with two constraints, energy and momentum, balancing simultaneously. Do the bookkeeping in words and tell me the condition.
Something moving at some speed makes an excitation of a certain momentum and a certain energy. The momentum comes out of the moving thing, so it slows a little, and the energy it loses by slowing has to cover the energy of the excitation. And how much does it lose? A heavy thing shedding a little momentum loses energy at a rate set by its own speed. The faster it is already going, the more each unit of momentum it hands over costs it. So the energy on offer is the speed times the momentum handed over. And the process is allowed only if that covers the excitation's energy.
Rearrange it.
The speed has to be at least the excitation's energy divided by its momentum. So for a given excitation, there is a minimum speed, below which making it is forbidden by conservation laws. Not unlikely, not slow, forbidden.
Now finish it, because there are many excitations, not one.
The flow could create any of them, so it is safe only if it is below the threshold for every single one. The critical velocity is the smallest value of energy over momentum, taken across the entire spectrum of excitations the liquid has.
And there is your geometry. Plot excitation energy against momentum. Momentum along the bottom, energy up the side. That is the dispersion curve. Energy divided by momentum is then the slope of the line joining the origin to a point on that curve. So take a line through the origin, start it flat along the momentum axis, and rotate it up until it first touches the curve. The slope where it touches is the critical velocity. Nothing about helium has entered. Any system, any dispersion curve, same construction.
Run it on the easiest case, a liquid whose only excitations are sound waves, energy proportional to momentum, a straight line through the origin.
Every point on that curve gives the same ratio. The rotating line touches all of it at once, and the critical velocity is the sound speed. In helium, about 240 meters a second. Now a case that ought to be better still, and I want your prediction before you do the construction. Take an ideal Bose gas, bosons with no interaction whatsoever, every one of them piled into the lowest state. Perfect condensation, perfect phase coherence, nothing in the way. What is its critical velocity?
Enormous, surely. That is the pure case. It is what London was computing, and helium is the messy approximation to it. Every atom in one state, and no repulsion to complicate anything. If anything deserves to be a perfect superfluid, that does.
Do the construction.
The excitations of a free particle. Energy going as momentum squared over twice the mass, so energy divided by momentum is momentum over twice the mass. And that goes to zero as the momentum goes to zero. The rotating line touches the curve at the origin itself tangentially. The minimum is zero. The critical velocity of an ideal Bose gas is zero. It is not a superfluid at any speed at all.
At any speed at all. And you have walked into the most important correction in this hour, so let us stand in it. Bose-Einstein condensation is not superfluidity. Condensation gives you macroscopic occupation and a coherent phase. It does not give you flow without dissipation. Now find what is missing because you derived it 20 minutes ago and never spent it.
Sound. The interaction gave the condensate a stiffness. Stiffness gives you sound, and sound means energy rising in proportion to momentum, straight out of the origin, a line of finite slope. And a finite slope is a critical velocity. Take the interaction away and there is no stiffness, so no sound, so nothing holds the curve up near the origin and it sags onto the axis as momentum squared.
Which is Bogoliubov's spectrum, assembled by you rather than handed to you. And it is why Landau spent his life insisting the condensate picture was not the explanation. He overstated it. The two ideas belong together, and we now know how, but what he was defending is what you just built. Superfluidity is a statement about the shape of the excitation spectrum, and a non-interacting gas has the wrong shape.
Then helium spectrum is not a straight line either, or you would have let me keep the sound speed.
It is not, and how Landau found out is my favorite piece of reasoning in low-temperature physics, because he did it with a thermometer. 1941, his paper on the theory of superfluidity. A gas of sound waves gives a heat capacity dying as the cube of the temperature, the count of how many modes you can afford. Helium's measured heat capacity has that piece and something else on top of it, and a linear spectrum cannot produce the something else.
What shape is the something else? A heat capacity is a very indirect way to see an excitation.
Indirect and completely decisive, and you can read it yourself. Suppose a system has excitations costing a minimum energy, a gap in the word we settled on. At a temperature well below the gap, how many are awake?
Exponentially few. The Boltzmann factor is an exponential of minus the gap over the temperature, and at low temperature that is brutal. So the contribution to the heat capacity would not be a power of temperature at all. It would be an exponential, dying far faster than any power as you cool.
And an exponential in the data is unmistakable, because nothing else looks like one. Landau saw an exponential sitting on the cube and read the gap off it, about 8.5 Kelvin in temperature units. So he proposed a second kind of excitation with a minimum energy and called them rotons, because his first guess was that they were something like microscopic vortex rings. The name stuck. The guess did not.
A second branch or a dip in the same curve. Those are different claims, and the geometry cares which.
Right to separate them. By 1947, he had it as one curve, rising linearly from the origin as phonons, bending over, coming back down to a minimum at a particular momentum, and rising again beyond. The minimum is the roton, at a momentum of about 2 per angstrom.
Convert that for me, because momentum in inverse angstroms means nothing to my hands.
A wavelength of roughly 3 angstroms, which is the spacing between helium atoms in the liquid. So a roton is not an exotic new particle. It is the cheapest disturbance you can make at the wavelength of the liquid's own graininess. Feynman's argument from 1954 is the one to carry. The energy of an excitation of a given wavelength is the free particle energy, divided by how strongly the liquid is already correlated at that wavelength. and a liquid is most strongly correlated at the spacing of its own atoms. That is what makes it a liquid rather than a gas. So the curve dips where the liquid is most structured.
Now the construction with the dip in it. My rotating line comes up off the axis and grazes the low point rather than the origin.
At, or very near, the roton minimum. So the critical velocity is the roton's energy divided by its momentum, and that is about 60 meters a second, not 240. The whole prediction rested on a heat capacity, which is why I made you read the exponential.
Was the curve ever seen directly? Fitting a dip to a thermometer reading is an inference, however good.
It was drawn by exactly the probe from last time. Neutrons, the same coincidence of the masses, an Ångström scale wavelength, and a millielectron-volt scale energy, so one particle resolves structure and excitation at once. Fire a beam at liquid helium, select what comes out at a chosen angle and energy, and the differences went into one excitation of known energy and momentum. Palevsky and colleagues found the roton region in 1957. Henshaw and Woods mapped the curve at Chalk River in 1961. A curve fitted to a heat capacity, drawn point by point 20 years later.
So helium stops being a superfluid at 60 meters a second, slower than its own sound, faster than anything I could pour. That is the number to carry.
It is not the number, and here I take something back from you. Push helium through a channel and measure where the flow starts to dissipate, and you get centimeters per second, sometimes millimeters. 3 or 4 orders of magnitude below Landau's value in almost every geometry anybody has tried.
Then the argument is wrong. You handed me a construction, I ran it, and the answer is out by a factor of 1,000.
The argument is right and incomplete, and the distinction is the point. Landau gives you a speed below which dissipation is forbidden outright by conservation laws, an upper bound on the critical velocity, and a very good one. It says nothing about whether some cheaper process is available first. One is.
The vortex. You put a line in the fluid 20 minutes ago and then left it standing there.
And now it has a job. A vortex line is an excitation too, an energy and a momentum, and not on the curve we drew, which was for small ripples. Nucleate one at a rough patch on the wall, let it grow, let it move across the flow, and it carries momentum out of the superfluid. Once one exists, others follow. That is what breaks at a centimeter a second.
If the vortex is cheaper, why does anything survive at all? A cheaper decay channel is normally the end of the story.
Because there is a barrier in front of it, and that argument now acquires a size. Take helium going round a ring-shaped channel. To lose one turn of winding, a vortex line has to cross the channel from wall to wall. The phase slips by exactly one turn as it passes, and it can do that because the phase is undefined on the core.
So the vortex has to travel the entire width of the sample, and it costs energy the whole way. What sets the cost?
That a vortex is not a local object. Add up the kinetic energy of the fluid circling it, shell by shell outwards. Each shell holds less than the last, but the sum keeps creeping up. It grows with the logarithm of how far the circulation reaches. Take that count from me, short but algebra. Multiply the energy per unit length by the width of the channel, and you have a barrier scaling with the container. Now say what superflow is in a form that would survive a hostile question.
A superfluid current is metastable, not stable. Friction has not been abolished. There is a decay channel, and it is a vortex crossing the flow. The barrier on that channel grows with the size of the sample, so at low temperature the rate of getting over it is unmeasurably small. Persistent, not perpetual, and it cannot leak away gradually because the current is labelled by an integer and there is no small change available to it.
Entirely right, and hold the shape. It is the answer we give again for superconductors, for the quantum Hall plateaus, for topological protection. Something is quantized, so it cannot change continuously. Changing it discontinuously needs a specific object to cross the sample. That object costs an energy growing with the sample. Robustness in 3 sentences, no magic anywhere.
Has anybody ever caught helium breaking at Landau's speed rather than the vortex speed? Otherwise, the roton calculation is elegant and idle.
It has been caught, and the trick is an object too small to make a vortex easily. Drag a single negative ion, an electron in a bubble it has dug for itself, through isotopically pure helium at about 80 millikelvin and measure its drift speed. Below a threshold, it accelerates freely. Above it, the ion sheds rotons and the drift speed pins. Tom Ellis and Peter McClintock at Lancaster measured that threshold in 1985, over 13 to 25 bar, about 46 meters a second at the top of the range, rising as you let the pressure off and extrapolating to Landau's 60 at 0 pressure, tracking the way the roton minimum shifts. And they had to squeeze the liquid above about 10 bar to see it at all, because below that the ion makes a vortex ring first. The cheap channel again.
Back to the bucket then. You said above some rotation rate, something else happens.
Vortices happen, and the argument is Feynman's and completely visual. Spin the container faster and faster. The liquid would like to rotate with the walls and cannot do it smoothly because its velocity is the gradient of a phase. So what is the best imitation of solid body rotation available to something only allowed to circulate in whole units?
A great many little whirlpools, each carrying 1 unit, spread out evenly. Averaged over a region containing many of them, that looks like uniform rotation. And the faster I spin the bucket, the more of them I need.
More of them, in strict proportion to the rotation rate. The number per unit area is the rotation rate divided by half the quantum of circulation. And parallel vortices repel, so they settle onto a triangular lattice, as mutually repelling lines in a plane always do.
Is that a picture or a photograph? I would believe a vortex lattice far more readily if somebody had taken one.
In helium it was inferred for decades. Hall and Vinnan showed in 1956 that rotating helium damps second sound in a way only a forest of vortex lines explains. In the cold gases, it is a photograph. Stir a trapped condensate with a laser beam and look. Madison, Chevy, Volibin and Dalibard at the École Normale did it at the turn of the millennium, and Abo Scheer, Raman, Vogels and Ketteler at MIT published a triangular lattice of over 100 vortices in Science in 2001. Rows of dark dots in a bright cloud, each a line where the density is 0 and the phase runs once round.
There is something I have been sitting on since the beginning. Kapitsa pushed helium through a gap and found no viscosity, but hang a disk in helium below the lambda point and twist it, and it feels a drag. Same liquid, same temperature, 2 answers.
And that contradiction is older than the theory. People were measuring a finite viscosity with oscillating disks in the very year Kapitsa measured essentially 0 through a slit. The resolution is the 2-fluid model, and it arrived twice. Laszlo Tisza proposed it within months of London's paper in 1938 from the condensate picture. Landau built his in 1941 from the excitation spectrum, rejecting Tisza's foundations while keeping the structure.
State the model and be careful about what it claims physically, because 2 fluids sounds like 2 kinds of atom, and that cannot be right.
It is not right, and the warning is worth its minute. There are not 2 kinds of helium atom, and no way even in principle to ask which fluid a given atom belongs to. What the model says is that the liquid's motion has 2 independent parts, which can move differently in the same place at the same time. One carries all the entropy and all the viscosity, the other carries neither. In Landau's version, the normal part is not atoms at all. It is the gas of excitations, phonons and rotons, thermally created, bumping into the walls and doing everything a viscous fluid does.
Which explains the temperature dependence immediately. At absolute zero, there are no excitations. So the normal fraction is zero and the whole liquid is super. Warm it and the excitation gas grows, so the normal fraction grows, until at the lambda point, the superfluid part is gone.
And that curve can be measured directly rather than inferred. Elefter Andronikashvili in Kapitsa's Institute in Moscow, 1946. A stack of thin metal discs, closely spaced, hung on a torsion fiber in the helium and set twisting. The normal fluid between the discs is viscous, so it is dragged along and adds its mass to the pendulum. The superfluid slips between them and adds nothing. Measure the period against temperature and you read the normal density off directly. It does exactly what you just said it must.
That gives me the fountain effect, I think. The superfluid carries no entropy, that is in the statement of the model. So join two vessels by a plug, the superfluid can pass and the normal fluid cannot, and heat one side.
Finish it.
Heating one side raises its entropy per unit mass. Superfluid flows in from the cold side because that is the only component that can get through the plug, and it dilutes the entropy on the hot side. But it cannot carry entropy back the other way, so nothing balances it. Fluid keeps piling into the hot vessel, and the pressure rises until liquid is forced out of the top.
In a jet, tens of centimeters high, driven by a heater no bigger than a torch bulb. Allen and Jones, 1938, the packed powder plug is the superleak. The light beam is the heater, and the fountain goes up. It is a direct reading of the sentence, the superfluid carries no entropy.
And the model must predict a second kind of sound, since there are now two things that can move.
It must, and this is the prediction that made people believe it. Two modes, then. In the first, both components move together. The total density oscillates, which is an ordinary pressure wave. First sound, about 240 meters a second. In the second, they move in opposite directions, with the total density held fixed.
So nothing moves in bulk, but the ratio of normal to superfluid oscillates from place to place, and that ratio is set by the temperature. So it is a wave in which the temperature oscillates and the density does not.
Heat propagating as a wave rather than diffusing, which is not something heat does anywhere else in nature. Second sound, and its speed is quite different, about 20 meters a second near 1.7 Kelvin. Landau's equations predicted it, Lifshitz worked out how to excite it, a heater rather than a loudspeaker, a thermometer rather than a microphone, and Vasily Peshkov measured it in Moscow in 1944, in the middle of the war.
A second sound in the same liquid, audible only to a thermometer.
And now a correction I have been saving. You said at absolute zero, the whole liquid is superfluid, all of it.
Which the Andronikashvili curve says. The normal density goes to zero, so the superfluid density is the full density of the liquid.
All of it is superfluid, and the fraction of atoms actually sitting in the zero momentum state, the condensate, in London's sense, the thing Bose and Einstein computed, is about 1/10. You measure it by firing neutrons hard enough to knock one atom clean out of the liquid and reading the momentum it had. The same beam again, used harder. Measurements and calculations argue over the figure. The honest range is 7 to 14%. 9 atoms in 10 are not in the condensate, at absolute zero, where the superfluid fraction is exactly 1.
Those cannot both be measuring the same thing, and I have been treating them as one quantity for the last half hour. Where exactly did I run them together?
They are not the same thing, and conflating them is the commonest error in this subject. The condensate fraction is a question about occupation. How many atoms sit in the single lowest momentum state? The superfluid fraction is a question about response. How much of the liquid refuses to be dragged when you move the walls? In a dilute gas, the two are close. In helium, they differ by an order of magnitude because the strong interactions kick most of the atoms out of the zero momentum state while leaving the coherence of the phase intact.
And it is the phase that superflows, not the occupation, which is why a superfluid is a Bose-Einstein condensate, is a sentence I should stop saying.
Stop saying it. Coherence is what matters, and a system can be almost entirely coherent while most of its atoms are out of the lowest state.
Then helium-3, which I have been waiting for since our third conversation, where it was the textbook Fermi liquid. 2 protons, 1 neutron.
Which makes it a fermion, half-integer spin, and everything we have built collapses. 2 creation operators for the same state. Swap them, flip the sign, and the expression equals minus itself, so it is 0. There is no piling in. Helium-3 cannot condense as it stands, at any temperature, ever. Not harder, not needing more cooling. The state does not exist.
So what does it do instead? Because it does become a superfluid, and that is the fact I want explained.
It pairs first, and it can, because 2 helium-3 atoms attract each other at moderate range, exactly as 2 helium-4 atoms do. 2 fermions bound together make a composite of integer spin, and a gas of those can condense. The pairs behave as bosons, share a single phase, and the phase does everything you have watched it do all hour. Quantized circulation, vortices, a critical velocity, persistent currents.
What is the scale of it? Helium-4 goes at 2 Kelvin, and I would expect pairing to be far more expensive.
2,000 times colder. About 9/10 of a millikelvin at 0 pressure, rising to about 2.5 at the melting pressure. That is the difference between a bath of liquid helium and a serious refrigeration problem, which is why it took 34 years longer to find.
Who found it, and did they know what they had?
They did not, which is what makes it a good story. Douglas Osheroff, a graduate student with David Lee and Robert Richardson at Cornell. The runs were the autumn of 1971, the papers 1972. They were compressing helium-3 along its melting curve, watching the pressure rise, and saw 2 small kinks in the trace, which they first put down to something in the solid. It took months, and other people's magnetic resonance work, to establish that the kinks were transitions in the liquid. Nobel Prize in 1996.
2 of them. Helium-4 has 1. Why does helium-3 get a second?
Because of the shape of the pair, and here it stops being a simple analogy to helium-4. 2 helium-3 atoms have a hard core, so the pair cannot be a structureless bound state with both atoms in the same place. They have to orbit each other, keeping their distance. So the pair carries orbital angular momentum. And once the orbital part is odd under exchange, anti-symmetry forces the spin part to be symmetric. The 2 spins parallel rather than opposed.
A pair with an orbital axis and a spin axis. So the order parameter is not one complex number anymore.
Not remotely. It is an object with a direction for the spin, a direction for the orbit, and a phase. And the ways of combining those are many. 2 are realized in the bulk liquid, and they are the 2 kinks. One in which the pairs share a common orbital axis and only the parallel spin combinations form. Another in which all the spin combinations are present and the arrangement is isotropic. Different broken symmetries, different modes, textures you can see with magnetic resonance.
Which is Landau's recipe applied to a far richer trough. Count the flat directions and you get the modes. Only the trough here is not a circle.
The identical recipe. And helium-3 is where people go to watch a complicated order parameter behave. No impurities, no lattice. It is also the cleanest evidence for the mechanism next time runs on. Fermions pairing up to make a superfluid. Because here there is no charge in the problem to confuse the issue.
And the last strand. You have been promising the cold gases every 10 minutes.
1995. 70 years after Einstein's prediction, and the first one made on purpose. Eric Cornell and Carl Wyman at Giller in Boulder on the 5th of June. About 2,000 rubidium atoms in a magnetic trap, cooled by laser light and then by evaporation, the condensate appearing at 170 nanokelvin. 4 months later, Kettley's group at MIT had one in sodium with 100 times as many atoms. Nobel in 2001.
Why does that count as a new thing rather than a colder version of helium? The physics you have described is the same physics.
Because of what you can set, which is what designed means here. You can tune the interaction itself. A magnetic field near a resonance with a molecular state runs the repulsion between atoms from strong through exactly zero to attractive continuously while you watch. You can squeeze the cloud with laser light until it is effectively two-dimensional, which is how you test Mermin and Wagner in a laboratory. And you can put the gas in a standing wave of light, a crystal with no defects and a lattice spacing you choose.
And the density is low enough that the equation we built is actually valid rather than a caricature.
Which is the fourth thing, and perhaps the most important. The volume each atom has to itself is about 1,000,000 times the volume the force reaches, so each really does see only an average, and the equation is quantitative. You predict the shape of the cloud, the speed of sound in it, and how it expands when the trap is switched off, and photograph all three.
What is the cost? Something has to be worse, or nobody would still be filling cryostats with helium.
Density and temperature. A condensate of 1,000,000 atoms is roughly 100,000 times more dilute than air. The energy scales are nanokelvin, and it lives for seconds. And nothing in it is strongly correlated the way liquid helium is. The gases give you control. Helium gives you the hard case. Neither replaces the other.
Something is bothering me about the shape of the hour. We began with a symmetry nobody can point at, an angle with no physical meaning, and ended with photographs of vortex lattices and jets of liquid going over the rim of a beaker. Is that phase real, or is it an extremely productive piece of bookkeeping?
Ask what would settle it, and you answer yourself. What would you have to see for the phase to be a real physical variable?
Interference. If two separately prepared lumps of superfluid have their own phases, then bringing them together should show the difference between those angles as fringes, bright and dark bands where they add and cancel. And since nothing ever set those phases, the pattern should sit somewhere different every time I repeat it.
Which is what was done a year and a half after the first condensates. Andrews and Kettley's group at MIT in Science at the end of January 1997. 2 independently made sodium clouds, released, allowed to overlap, photographed. High contrast fringes in a different position on every shot because each pair chose its own relative angle. That is, the wine bottle with a camera on it, not that you can read where a marble sits, but that you can see 2 marbles landed in different places, and the gap between them is different every time.
The order parameter photographed, and the beaker we opened with is a different object to me now, not a liquid finding its way over a rim, but an angle that agreed with itself across the glass. 3 things I could not have said this morning.
In whatever order you like.
Why superflow does not stop, with no magic in it. At absolute zero, the only way to slow the flow is to make an excitation, and energy and momentum together forbid that below a speed you find by rolling a line up from the origin until it grazes the dispersion curve. In helium, set by the roton dip, about 60 meters a second. But there is a cheaper route, a vortex crossing the flow, cheaper by 3 or 4 orders of magnitude in a real pipe. So the current is metastable, barred by an energy that grows with the container, because the vortex must travel the whole way across.
with the piece that makes it robust rather than merely slow.
That the current is labelled by a whole number, so no gradual leak is available, which is the second thing. Go once round a loop and the wave function must return to the value it had, so the phase can only have wound by a whole number of turns. The velocity is the rate the phase winds in space, times Planck's constant over the mass of one atom. So circulation round any loop is that whole number times about 10 to the -7th of a square metre per second. And where the winding is non-zero, the loop must enclose a line on which the density vanishes, because that is the only place an angle may be undefined.
And the third.
Helium-3 can do none of it. It is a fermion, so two of them cannot occupy one state. The sign convention from our second conversation, with no exceptions anywhere. There is no pile-up to be had, so it must build composite bosons first. And because two helium-3 atoms cannot overlap, the pair has to orbit rather than sit, which forces the spins parallel and gives the order parameter a spin axis and an orbital axis instead of a single angle. Hence 2000 times colder, and two phases where helium-4 has one.
3 for 3. You were not 3 for 3 on the ideal Bose gas.
I did not, and that is the thing I will actually keep. I said a gas with no interactions would be the perfect superfluid, and the construction you had just handed me said its critical velocity is 0. Condensation is not superfluidity. The interaction I wanted out of the way is what gives the curve a slope at the origin, where a free particle has none. And that slope is what makes flow possible.
Which is the emergence claim in its sharpest form so far, and it is where I want you standing rather than on any of the phenomena. Non-interacting bosons, a condensate and nothing flows. Interacting bosons, a condensate, a linear spectrum, a roton, quantized circulation, vortex lattices, two sound speeds, and a liquid that empties a beaker over its own rim. The ingredients are a hard core and Bose statistics, and neither mentions flow.
And next time the particles that have to pair are charged.
Charged, and every step of today is redone with that one change. The phase now couples to the electromagnetic field, so the gapless mode we manufactured last time is bought off, pushed up to finite energy, and the photon acquires a mass inside the material. The circulation quantum picks up a factor of 2, and that 2 is a direct measurement that the things going round are pairs. And where helium-3's atoms attract to begin with, 2 electrons in a metal repel, so something must arrange the pairing against a force pointing the wrong way. Finding out what took 30 years, and it is the whole of the next hour.